Let's continue with where we left off last time in the previous video clip, where I introduced you to how a graded potential is actually generated and how it travels away from the point of origin. So this diagram here is sort of a simplified version of what we looked at before. Again, imagine that this represents a portion of a dendrite that serves as the postsynaptic membrane. Neurotransmitters are diffusing across the synaptic cleft and have begun to bind to their chemically gated ion channels, which allows for the influx of primarily sodium, some efflux of potassium. But essentially what's happening is that this section of our dendrite depolarizes, and slowly but surely the depolarization wave spreads, and it spreads away from the point of origin. So we're going to see that the depolarization spreads towards the axon and the depolarization wave spreads away from the axon. Clearly, we would like for as much depolarization to travel towards the axon such that we hopefully can reach the axon hillock and depolarize it by at least 15 millivolts to open up those voltage-gated ion channels and therefore fire an action potential, assuming then that many graded potentials are generated through the binding of more and more neurotransmitters that cause depolarization. Now there are a few more things we need to address here with regards to the traveling away from the point of stimulus, the traveling away of the depolarization wave. That is the movement of the graded potential called the local current or longitudinal current or capacitance current. And that is the following. Despite the fact that we need to remember that there are chemically gated channels all along the cell membrane of a dendrite, I'll draw a few more. We have also along any cell membrane the presence of leakage channels, and I will indicate those as follows in the orange. And these are channels through which the ions that are of special interest to us, such as sodium and potassium and even chloride and calcium, but particularly sodium and potassium, they are constantly leaking through those channels. And you need to assume that these proteins, these ions, are everywhere in between these chemically gated ion channels. And how is it that the ions travel through these leakage channels? Well, they're called leakage for a reason. The ions literally move along their concentration gradient through these channels by means of diffusion. In addition then, we find that there are also pumps, and I'll illustrate those as little circles everywhere. Our sodium-potassium pumps are mixed in all of this as well. Okay, so where does that lead us then? Well, first of all, as our graded potential starts to migrate away from its point of origin by the positive and negative ions trading places both on the inside of our cell membrane and on the outside of our cell membrane in both directions, away from the axon and towards the axon, at the same time we see that plenty of ions are going to be leaking through the leakage channels. So we see that ions leak through the ion channels depending on their concentration gradients. And because of that, because of these leakage channels, we find that the strength of our graded potential diminishes as we travel away or as we move away from the point of stimulus. So the further away we are, strength of graded potential decreases the further away from point of stimulus or point of origin. Clearly that could impact our concentration gradients as well as our electrical gradients, but remember we always have the sodium-potassium pumping all of the sodium and potassium ions at least in such a direction to where the concentration gradients for those ions are not going to be disturbed all that much. But if we were to now illustrate a graded potential with showing on the y-axis, oops, I keep doing that, sorry about that. On the y-axis we're going to label the potential's strength in millivolts, and on the x-axis we're going to indicate the distance along, let's say, the dendrite. Then we find that if my arrow here indicates where the origin is of the graded potential, we would therefore have the highest point of our graded potential, and as we move away from that point of stimulus, we should see that the strength of the graded potential diminishes, like so. And so therefore we say that graded potentials are decremental, meaning that they lose strength with distance. That is not to be confused with graded potentials being graded. Graded potentials are said to be graded because they can be strong or weak. So they can be strong in voltage or weak in voltage. And because of that, they are called graded. So they have a level of gradation to them. This is not at all the case for action potentials, which are all or none responses, and they occur with the same strength at all times. Remember, these graded potentials must make it as a group, hopefully, and summated all the way to the axon hillock in order to cause a change in voltage that is strong enough to open up the voltage-gated channels. But before we talk more about summation at the axon hillock, let me remind you that graded potentials are not always depolarizing graded potentials. The one that I'm showing here is an example of a depolarizing graded potential, because we're allowing for positively charged particles primarily to flow in rapidly upon binding of a neurotransmitter. And these positively charged particles, of course, are sodium. But we can also generate hyperpolarizing graded potentials. And we're going to take a look at that next.